Welcome, everyone. Thank you for joining the Ceratec webinar, Simulating Drop Loads Impact on a Structure with FEMAP and NX NASTRAN, Part 2. I would now like to introduce John LaCour, Ceratec's application engineer, who's based out of Texas. John, you can take it from here.
Okay. I'm going to do kind of the second part of the simulated drop load using FEMAP and NX NASTRAN. And the last time we go to we analyzed using linear and using a rigid mass and spidering it with R bars to simulate that. You know, the simplest way to simulate it and get some idea, because I did show that we could run a static and look at the load, the static load on the structure, but then we could run a dynamic load and you can actually see an increase in load. So it kind of gives you some idea of what's going on during an impact. Now, for this one, we're going to have a more complicated solution. I'm going to use a nonlinear transient solution, and why I'm going to do that, why what it was calling for nonlinear transient, I'm going to use gap elements. So the stiffness is going to change when contact is made, and so therefore I have no other option but to go nonlinear transient. And I'm going to kind of change this up. I saw some comments. People are saying, can you use instead of a rigid structure, you could use a flexible structure and simulate this. The structure that's doing the impact. And I said, sure. So I kind of changed it up so I could demonstrate that as well. What I'm going to do is I'm going to create the interface. I need to create an interface. I'm going to use the RBE3s and CBush. That is, I'm going to show you the right way to do it and then the wrong way to do it, or first the wrong way to do it and then the right way to do it. And then I'm going to run a linear, nonlinear transient to simulate the contact conditions, and we'll compare the results. So yeah, the previous I used actually an RBE3 and a solution 109 with initial conditions and gravity, and here's how I calculated the initial velocity at the impact for the previous webinar. And if that doesn't jog your memory, this will, because this is actually what we looked at here with the rigid mass here, and then the RBE3 spidering down to the contact area. So here's what we're going to do on this one. We're going to actually, same structure, same footprint, but I'm going to put a box on there, and the mass is different. So I'm kind of starting from the beginning of doing comparisons with a static and, a static and transient, but that's fine. So this is a chart we saw before the last one. What I'm going to be doing is dropping this box here. I'm going to drop it 1 unit. In this case, I'm working in inches, so I'm going to drop it 1 inch, and here's the acceleration. Initial velocity is 0. And so I'm going to use this equation to calculate the velocity at impact, and it happens to be 27.8. Kind of put that to memory, the 27.8. And also, I'm going to be using rigid elements. I'm going to be using rigid elements to connect it. I'm going to be using CBush to connect it. I could use contact to connect it. Contact works on static, but it doesn't work on nonlinear transients. So, but it will work on advanced nonlinear. In this case, I did not do the advanced nonlinear. I don't think it was necessary to do the advanced nonlinear, and it takes a lot longer to run advanced nonlinear because you're using a lot of features in there that you really don't need to use for the nonlinear contact. So before I go off and do a gap element, it's important to know the orientation, because FEMAP will ask you for orientation, okay? So what I'm going to be doing is a kind of a nifty quick way, and I'll show you just a little bit, to connect up the contact surfaces via FEMAP, but it's going to ask me for orientation vector. It's going to ask me for this vector here for the sole purpose of determining your Z direction and your Y direction elements. You will have spring in this direction, and you'll have a spring in this direction and this direction, and you'll see it in FEMAP how it specifies that, but it's important to know how to set up this vector right here. Also, I'm going to actually put in a spring element, a CBush that is, and it's going to ask me for the vector there. It's just the same thing. Diagram's a little bit different, but we see the X direction stiffness is here and the Y and Z directions this way. And so there is our vector that it's going to ask us for. And so with that, let me step out of here and step over to FEMAP. And here's my basic structure right here with the same platform with a box sitting on the top. And I need to create a contact surface right now. Right now it's very busy. And a matter of fact, I have created some groups here to help simplify this. I'm going to activate that. There's my box, there's my frame, and there's my contact surface, okay? So here's the two surfaces I want to contact right here. So what I want to do, in one case, I want to put R bars across there to connect it together. And then another case, I want to put springs across there. And then another case, I'm going to put gap elements. So FEMAP and the meshing has this little nifty thing right here. Let's see, connect right here, closest link. And this works great because it works great when both are set up and are symmetrical. I have the same number of nodes on both surfaces. They have the same dimensions, so it's going to work perfect. If the nodes were different or the dimensions were off, it would cause some problems. Especially if the nodes were off, it would cause some problems. So when you create these contact surfaces, make sure that the node count and the dimensions are roughly, or the node count's the same and the dimensions are roughly the same. So what it's asked me here, let me just pull this up. It's asked me to select the nodes to generate from. So I want to come in here and say on the surface. So, and that's 2. So, and then it says select nodes to generate 2, and I want to go again the surface, and I select the bottom surface and I say OK, and I want rigid elements in this case. So I'm going to do this right here, and I'm going to say OK, and I should have, but I didn't. I should have say automatically add. Now what I can do is come back and undo that. And I can come here and say automatically add, which I usually forget to do. So let's just do it again. Oops. Reset. I want the top surface. And surface, I want the bottom surface. And I want rigid elements. Let's hope I did this right. Okay, there, it connected it up. See, and then I put on automatically add to the group so we can see it. So that's a pretty easy one there. So let me undo this, and let's go to, I'm going to do gap elements. Actually, gap elements and spring elements, the orientation is roughly the same. So I'm just going to do gap elements. So I'm going to go back to my mesh, connect closest link. I'm going to go through the same thing. Surface, I want this top surface here. And then I'm going to select the bottom surface. And in this, I'm going to create a line element. And, oops, I need to create a gap element here. But let's see, I can come here and go right here to gap. And so I can go ahead and put my properties in here. I'm just going to put some stuff in here. Remember we talked about the compression and the stiffness and the X direction. This is where we'd put this. Let me just talk about this. I have this up there. Compression stiffness is the stiffness when it makes contact. Okay, and we'll talk about how to estimate that. Tension stiffness is when it breaks contact. So what stiffness does it have? 0. Okay. And then the transverse stiffness is the shear of these planes. So I'm going to put just some value. It's going to be less, and the friction coefficient. So I'm going to put this for friction coefficient, and that's about all you need to do with this. So I'm going to say OK, and say OK here, and then it asks me for the orientation vector. Okay, so I could do an orientation across here. I can do it. I choose to kind of use the nodes. And this is asking for coordinates points. So let me just go to nodes. I'm going to select this node, and then I'm going to select this node right there. Okay, so this is going to be my vector, my orientation vector, and my Y and my Z should be in this plane. I'm not too worried about it because which one's Y and which one's Z, because they're both going to have the same stiffness. So, and let's see there. So there my gaps are hooked up. and I can actually come in here and turn off my plates. I see some rigids are still in there. I can turn off my plates, and you can actually see the gap elements in there and the symbol for the gap element. So that it's ready to go. So that's it's really nice. So the first thing is I'm using gap elements, so I have springs. So at contact, I'm going to have a spring constant or springs in between there. So I wanted to figure out what stiffness I need for the springs, and so at the simplest, I want to make sure that these since I'm running a transient, it is dynamic, and I want to make sure that there isn't any interaction between the box and the frame via the springs. Okay, I want these springs to be, I want the frequency to be way out of range of the other frequencies, so I have pretty much of a rigid contact here, but there'll be flexibility with the springs. So how do I do that? I ran a normal mode right here, okay? And so I can come in here and I'm going to actually animate this, okay? And I can kind of go through these, and I can see that now actually I didn't see this, but actually there's a little interaction that's going here, and probably I should have, or I would have, if I looked at this further, is stiffen these springs up so it would couple this together, and I wouldn't see this interaction that's going on right here. But that's what you do, is you kind of go through here and look at these mode shapes. See a little interaction, but it's mainly this is going on. Okay, so that's how you kind of determine how stiff your springs. I actually should have stiffened the springs up a little bit right here, but that's fine. The next thing is I want to find, for damping purposes, I want to find where the energy is going into the structure when it makes contact. And so this is the dynamic characteristics of the structure, the eigenvalues. So, I start going through this, and you have to kind of use engineering judgment here. When this box strikes this frame, is the energy going to go into this mode shape? Probably not. I mean, not probably not. It's not going into that mode shape. So you kind of go down here and look at how this box would respond with the frame when it makes contact. Now, I believe that, and I say that actually energy would go into this mode right here. And so it's we need to note that 67.6 hertz, okay? And so we just keep kind of going down through here. I'd say that energy would probably go into this mode as well. Now, what I did is I put a damping constant on this. I said most of the energy when it strikes this platform will go into this mode here. And so I need damping because that's what happens in the real world, and it's going to take energy out of the structure and damp it out. So I applied a damping coefficient to this frequency, and I had to do it that way because I'm running a direct. Now, it's interesting, as I ran this thing and I was looking at the frequencies, or looking at the response, I started looking at peak to peak. And actually this one, as it's ringing out, is not ringing out in this mode shape. I start seeing something at about 130, 135 hertz. And so I came down here and looked at that, and it's actually, this is the mode shape where it's actually ringing out. So if I was going to do this again, I would go and change my damping to probably 130 hertz to damp this out, to take the energy out in this mode shape, because that's where the energy is actually going, or most of it's going. So that's kind of how you select the modes, and I'll kind of show you what I did with that information as we move on to the contact. I kind of have it turned off. You can't see a lot here, but as soon as I turn the contours on, you'll be able to see more. But let me kind of take you over here and show you the damping, how I use that term. I'm going to open this up, this manager right here. So here's my damping. This is how you apply damping for a direct. It's the frequency for the system damping, and it was a 67.6. And I just had to run it several times to get a damping value where it actually damped out in 10, 12 cycles, and that's kind of where you have to use engineering judgment. I noticed it kept ringing out, and now that I identified that frequency, I probably should have put 130 here, okay? But you know, that's kind of how you do dynamics and how you get a more realistic and solution, and how you use engineering judgment. Okay. Also, it's what's important here is the time steps that it goes through here. You also want to remember in your time steps that you, whatever frequency, if it's 130 hertz, that your time step here is going to be, it's 130 cycles per second. So it's 1 over 130, and then I divide it by 10 to break it up into 10 to kind of give an idea of how many time steps you need. And that's, the world of dynamics, to make sure you capture that frequency and that you don't filter it out. So this, you got to pay a special attention here, and remember the number of time steps really adds up as the data that you get back. So I went ahead and ran this kind of the same way I ran the other one. I put initial condition on it. I have gravity on it. I put initial condition and I ran it. This is time 0, and right at 0.0004 seconds, we see a 25,000 psi here, and I can kind of keep going. Now we go to 43,000 psi and 15. So we have actually a maximum stress right here. Looks like the structure is just sitting here. The whole structure. I see a little color in here, but as I turn this thing around, I actually see some contact right here. It's essentially this box is welded to the structure, and it's actually these beams are very stiff. I have some I-beams across here, and they're very stiff, and they're actually taking the impact load. I don't think that's realistic, and so because the box really isn't welded to the structure. So, but I want to show you that. What I'm going to do now is take you to this one, same one. Now I have springs. I have put springs in there, and I'm going to open up my results, and I put initial velocity on it, and so I'm going to turn it on, and so we kind of see a deformation in here that's going on. We can look for a peak. As a matter of fact, it peaks right at the beginning, right about here. So it peaks right here, and I can turn it here, and I can look at the high stress in these corners right here. And as a matter of fact, I'm going to turn off this to get that out of the way. And so I'm kind of getting some the high peak stress right in here. It's really not high, 53, 5 KSI. It's really not bad. But you can see the high stress is probably higher here because it's a lot stiffer right here. And so this is the high stress. This is right at impact. And as I come down through this thing, we can see that the stress starts dissipating out, and actually the high stresses you start seeing the high stresses over in here and over here, and these stresses will be lower, and that's your typical impact. Okay, and so this is with a transient, and it actually didn't do that bad of a job. Okay, but now let's move over to my gap condition, and with the gap, it makes it a little more complicated with the showing displacements, deformed shapes, because this thing's dropping 1 inch, so it's this box displacements are just way out of line when you actually turn displacements on. But you can't look at it; you just have to. It kind of gets annoying with this box. So what I have this on is the right at impact, and I think it's let's look at its right. Oh, this is interesting. What I did is I dropped the box on this one. Let me take you over here to the loads. Actually I didn't turn on this initial velocity. I just turned on the gravity and had it 1 inch high and just let it go. Just let the box go and make contact. And so I want to know if that really made contact at my calculated velocity. And if you remember, I think it was 27.6 or 27.7, something like that, was what I calculated the velocity at impact. So we can see I dropped my box right here, and I hope you can see it as well as I can see it on my screen. We dropped the box right here, and it started out Z, and this is velocity. And it started right out here, and it came down to just a tad above 28, which would be 27 something, and then it made impact. So roughly the velocity that I calculated is the velocity that NX NASTRAN experienced during impact. So NASTRAN's doing a good job at simulating a rigid body drop. And so this was kind of verification that it actually impacted at the same velocity. And so so what it's going to do, it actually, I calculated it actually impacted at about 0.72. So I'm going to come over here, and we can see this is the unloaded stress on here for 1G, and we can keep coming down, and so we see actually there's our impact right here. And the time's going to be different because I dropped it 1 inch. So if I actually subtracted, 0.072 off of this, it impacted at 0.009 or 0.008 roughly. And so here's our maximum stress right here during impact. Let me zoom in here. I'm going to have to come in here and turn because the displacements, actually I can just turn that off. Let me come in here and turn the gaps off. And you can kind of see this very similar stresses in here due to the impact. But we do have higher stresses here due to the impact. And let me see if I can explain that. I'm going to bring back my, my plot right here. This is the new FEMAP 11 plot. And I'm going to come over here and turn this on. I'm going to point out two things here because I see we're running out of time. I see two spikes. I see a couple of spikes here where we have, this is accelerations in the y direction. We have some spikes here, and I think that's the reason we're seeing this high stress. And what I think is going on here with these spikes is when it makes contact, that is a very interesting dynamics of a structure. When you have two structures that have dynamic energy, and all of a sudden you connect them together, and all of a sudden they're redistributing the energy at that contact, okay? And I think that's what's creating the spike. Whether it's realistic, I would say right now it's not realistic. I think that's just the dynamics of the simulation as it's making contact. And why I say it's not realistic is because it's going to, the contact is not a contact where it's really tied together. There's slippage in there. There's some friction. And so, but you know, I think you will see a little bit higher stress due to contact. And another thing here is at this point we could kind of come to the conclusion that, you know, the transient and the nonlinear are probably given fairly close results, and they are. We're seeing a little bit higher stresses with the nonlinear, and so it's doing a good job. And so why it's doing a good job is that the box never breaks contact with the structure. If we can kind of see down here, even though these are some spikes, and I think that's just due to the simulation of the contact connecting up, and we see a little spike in this node point that I selected here. But really, the acceleration of the whole box is probably right down in here, because this is the box side. And so it probably never gets above 200 inches per second squared. In order for the box to break contact, that is to bounce off, it would have to exceed acceleration, which is 386.4, I believe, is the acceleration inches per second squared. So it would have to exceed that to actually pop off of the, you know, to pop off and then come back down and make contact. And so that's so we're not seeing that. So this is kind of a good thing to look at to see if we really needed to do a nonlinear or not, if we're really seeing accelerations at that interface that exceed gravity, where it would cause the box to lift off of the platform. And so we don't see that. So let me go back to my presentation here. And so the transient solution with initial conditions, as I said before, will only run in a direct solution. The simulation I simulated the box frame with interface with springs, and because the box did not separate, the linear transient solution produced good results, and I think it actually did produce good results. However, higher stresses are seen due to contact dynamics, and you know, I think I'd be comfortable with these low stresses of running a transient and not going to nonlinear. If the box separated from the frame during simulations, a nonlinear would be the only solution. And so when you're running this in a transient, you're going to need to go look at the accelerations on the box to see if those accelerations are exceeding gravity, and then you know the box is separating. Then you need to run over here and run the nonlinear. And again, one other caveat I'm going to leave you with is one must fully understand NX NASTRAN dynamics to get good results, because we had to do some dynamic assessment with springs and choosing frequencies and choosing damping and choosing time steps to get good results. So keep that in mind when you're running dynamics. And so I'll turn it back over to Emmy.
Thank you, John. Okay, let's see. Just want to thank you. You did a great job. I'm going to go ahead and leave control to you at the moment, John, just in case you need to show something with any of the questions. So we'll now begin the question and answer session for everyone. So if you have a question, please enter it at this time in your GoToWebinar control panel. So I have a question here. I see that this third analysis is with the gap elements. What were the first two analyses that you showed? One had rigid elements, possibly the first one, and second had something else.
The first one was rigid elements, okay? This is the rigid elements here, okay?
Okay.
And the second one, I ran a transient with springs. And I'm glad you asked that question, because I didn't make this clear. I used the same springs in here that I used with the gap elements, okay? So this is, what this is simulating here is the nonlinear at contact, okay? So this at contact, this is the same model. This is the same model at contact as the transient. And so in both ones, I use springs at the interface, and you have to use springs at the interface. It has to be connected together. So you can use bar elements. You can actually connect the right to the grid points, which I wouldn't do, because again, that's welding it. That's the same thing as R-barring it. So you need some flexibility in between there, and so that's why I use springs for this one. So I used R-bars, which showed bad results, high stresses. I used springs in the transient because that was the closest thing to the gap element. And in the gap element, at contact, it's springs.
All right, well, that's great. Thank you. Let's see, I do have another question. Can you use a connect surface on the model interface?
Only with advanced nonlinear. You cannot do it with the basic nonlinear, and so, or the transient. So you can use it with static, and you can use it with the advanced. And I was going to run it with the advanced. Its strength is its material properties, large deformations, and so I ran it, and I ran it for about 10 hours and said it wasn't worth it, And so, but it's probably going to give you closely the same results because, on the contact, when it makes contact, it connects the nodes together. That's how it does. So yes, I could have, but it'd been only in advanced nonlinear.
Okay, thank you. I have another question. How would this compare to an LS DYNA analysis or DYNA analysis?
Yeah, LS DYNA. I think this would have good results compared to LS DYNA, and the reason is that we're really in the linear range. LS DYNA's strength is damage. When you're exceeding yield and you have large geometric deformations, and I think it would give pretty close equivalent results to LS DYNA, because this isn't what you get LS DYNA for. You get LS DYNA for damage.
Okay, perfect. And one last question, John. Can you run a model solution to reduce the run time? Can you run a model solution to reduce the run time?
Yes. Well, yeah. There's reduce the run time, which I always do. Is again now what I do is let's see. I always come in here and I turn on to reduce the runtime. I mean, see, I'm running it direct, so I don't have the option of running modal to reduce it. Okay, so the only thing that I can do is use super elements, and maybe I will in a future webinar show you how to use super elements in here to reduce your model for nonlinear. But the other option is is to come in here, right here, and use multiprocessors right here. And you see that I got 12 processors on here, and I used 10 of them. And so that really cut down my runtime. And I would recommend that you always turn this on. By default, turn this on and turn on the number of many processors as you can.
This concludes our meeting for today. Thank you so much for joining and have a wonderful day.